and this. Okay, so guys, here's the scoop. Again, this is the first part of a two-part series. But guys, what I want to do is I want to show you what lab on Tuesday is going to be like. Hi. Oh, no, you're fine. Thank you. I have no idea what's in there. It's going to be...
Right down there.
Thank you. Oh, you're a hero. Thank you so much. Appreciate it. Oh, boy, 3 boxes. Well, I already said that. I know, see? So, guys, what I want to do is I want to show you what Tuesday is going to be like. Because, guys, when you walk into lab on Tuesday, up at the front of the table, there's going to be all of these chemicals spread across the front table. And when you walk in there, you're going to start doing all these reactions. I think 5 or 6 of them. It's actually a really neat lab. But then, guys, what you're going to have to be able to do as a result of this, which is what you're going to learn in the next 2 days, is this. So don't write this down, just watch. So, guys, imagine, if you can, the last lab that we did. And if we're thinking about the last lab that we did, what does that make this? A crucible. And guys, in that crucible, we put chunks of, what does that make this? Magnesium. And then we cook the bajinkers out of the magnesium for 15 minutes. And when we did, what did that turn into? White powder, right? And so, guys, as this was turning into white powder, what did you learn it was reacting with? The oxygen in the air. And so, guys, there's oxygen up here. There's magnesium in the bottom. You saw the reaction, and it turned into white ash. Here's what you're going to learn in the next couple days. How do you talk about that in an intelligent way? How do you represent what took place in your crucible? And guys, please don't write this down, but this is where you're going to be after Friday. So guys, it goes like this. We took some magnesium, which is Mg. Now guys, what did that magnesium look like? Do you remember? It was a strip and it was metal, and do you remember you ripped it up? Guys, that makes magnesium S, which means solid. Then, guys, the magnesium reacted with the oxygen. What phase is the oxygen? Gas. So, guys, we go like this, and I'm going to get rid of it here now. Guys, the oxygen is a gas. But guys, there's another thing that you need to know about oxygen, and maybe you know this. Guys, oxygen is crazy reactive. It really wanted to bond to the magnesium. All we had to do was heat it up, and it did. But guys, oxygen is so reactive that if it doesn't have something else to bond to, it will actually bond to itself in packages of 2. Did you guys know that? Like if you've ever seen athletes, like professional athletes, and they're resting on the bench and they're sucking oxygen through a mask, and have you ever heard them say that they're breathing O's? Have you ever heard, or is that never, perhaps? But guys, the reason they call them O's is because it's literally 2 oxygens bonded together. When you breathe in, you're actually bonding packages of oxygen in packages of 2. And one of the things that happens inside your lungs is they separate and then they absorb into your bloodstream. We'll talk about that more later. But guys, then when these things bonded together, they bonded magnesium to oxygen and they turned into that white stuff. Guys, what was the white stuff? Solid, liquid, or gas? It was a powder, which is a solid. So guys, that was a solid. So this is the beginning of it. This represents what took place inside of the crucible. But guys, do you see the problem with what's on the board? What's wrong with that? Talk about that, Talmadge. Yeah. Let me use your word, and I really like the way that Talmadge said this. He said, there should be another oxygen. Now, guys, when we talk about should be, that means you're calling on a rule. This is wrong because I know what should be right. So, guys, why should there be another oxygen? Says who? Why is that bad that there isn't? Say it again. The law of conservation of mass. Guys, we established a long time ago that matter's never created or destroyed. It doesn't go away. It doesn't just magically appear. It has to be there, and it's always been there, minus the Big Bang and the things that we learned about that. So guys, the problem is 2 oxygens are going in and only one's coming out. So guys, this is not the solution to the problem. See, magnesium is +2 and oxygen is -2. Therefore, we only need 1 of each. So guys, the solution to the problem is not to huck a 2 on the oxygen, because 1 magnesium does not bond to 2 oxygens. So what do we do to fix it? And the answer is this. Now we've got 2 oxygens, but now we've got another problem. There's 2 magnesiums. So now, guys, we put a 2 there, and this represents what happened inside the crucible. Now, guys, here's the deal. What I just did with you, you are not going to be able to do in its entirety until Friday. So, guys, there's 3 steps to this. We're going to do 1 and 2 today. We'll do 3 on Friday, and then we'll get you into lab on Tuesday. You guys good to go? Do you understand what we're up to? Okay, so guys, this then is how this is going to play out. Guys, in order to get you there, holy smokes, in order to get you there, guys, there are some foundational thoughts that we need to share, and this goes in your notes up top. I will be very helpful in terms of telling you what to and not to write down. But guys, fundamentally, this is it. We are going to learn to balance chemical equations. So guys, what is a chemical equation? This is a chemical equation. An equation like 2Mg plus O2 yields 2MgO. Guys, that is a statement that represents a reaction. And that's what chemical equations are. They are statements that represent reactions. Now, guys, here's the trick. These things have parts, and you need to know these terms. When we write chemical equations, the stuff that is going in we call the reactants. Makes sense, right? They're reacting together. Then, guys, we separate the reactants with an arrow. And this stuff is important. This you want to get in your notes. Guys, the arrow we read as the word yields. And then the other side of the reaction is the stuff that's being produced. We call those the products. So reactants yield products. Now, guys, here's the interesting bit. The products are not always on the right, and the reactants are not always on the left. So how do we always know which ones are the products? The arrow points at them. So, guys, if that doesn't make sense to you, you can certainly scratch it down. The arrow always points at the products. So, guys, that is foundational thought number 1. You ready for foundational thought number 2? Grab your periodic tables. Come on. Come on. Am I the only one that's curious about what's in here? I will, just not yet. No. No. You guys are the kids that peek at your presents at Christmas, aren't you? Liars. Guys, foundational thought number 2 is about to come up on the board. It is this. Write it down. Diatomic molecules. Guys, I would propose to you that defining what a diatomic molecule is a waste of your time, because you can figure it out just by reading it. What does di mean? 2. What does atomic mean? Atoms. What are molecules? Covalently bonded. So it's molecules made of 2 atoms. If you've already figured that out, it's a waste of your time to write down molecules composed of 2 of the same atom. It's in the name. But guys, here's the trick, and I would encourage you not to write this down either. Oxygen is not the only one that does this. When we wrote our previous balanced equation, and this is going to get sloppy, but guys, when we wrote that, we put a 2 on the oxygen because we said that oxygen is so reactive that it bonds to itself. Well, guys, it turns out oxygen is, don't write this down, oxygen is not the only one that does. There are 7 of them, and you need to know them. This you want to include in your notes. Guys, the 7 elements that are diatomic are iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. Now guys, you'll notice that I've memorized those. You need to know them as well. Again, as they are on the board, iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. But guys, I would propose to you, and looking at your eyes, I love that some of you are already there. Guys, as you glance at your periodic table, if you see the pattern, you don't have to memorize them. Do you see the pattern? See it? No? Yeah? So guys, do this. Start at iodine, go up till you can't, go left till you run out of red, and then jump to the only other red guy on the left. So it's up, over, hop. Iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. You good? Guys, if you're curious, because I know you guys are, that is not a coincidence. Why are these the elements that are the diatomics? And guys, the answer is because, first of all, it's the halogens. And the halogens are 1 electron away from a complete octet. So they're just looking for 1 more electron, and they grab them from each other. Then guys, oxygen, nitrogen, and hydrogen are so ridiculously electronegative that they bond to each other as well. Those are the 7. You just need to keep track of them. You guys good? Okay, guys, now we're done with foundational thoughts. Now, guys, what it's time to do is lay out the steps that we are going to use to balance equations. Guys, this is your last page of notes. You ready to go? So, guys, first of all this. Why do we have to balance equations? And the answer is the law of conservation of mass. But I pray that you're not writing this down because you already know what the law of conservation of mass says. What does it say? Matter is never created or destroyed. So guys, if matter is never created or destroyed, therefore the number of atoms that go in have got to equal the number of atoms that come out, because if they don't, we're destroying or creating matter. So guys, because this is important, this is where you want to start writing this down. These are the steps for doing what you need to be able to do. Now guys, what you're going to see is this. There are 3 steps. And then after I've given you the 3 steps, I'm going to allow you to benefit from my years of experience, and I'm going to give you some hints. Guys, things that will make these easier. Then we're going to model this for you, and then I'm going to get out of the way, and you guys are just going to spend the rest of the day practicing, because that's really the way to learn these. So guys, it goes like this. Step number 1 is this. Identify the reactants and products. Now guys, here's the thing. This is hard. This is so hard that we're not going to do this today. We are going to do this on Friday. So you're going, wait a minute. If this is hard and it's step 1, I can't go on to step 2 if I can't do step 1. Guys, that's true. What that means is I'm going to do step 1 for you. And then on Friday, you're going to do it on your own. But I will do it for you today. Step 2 then is this. Write the chemical formulas for the reactants and products. Now guys, here's the tricky bit. You took an entire test over this 2 units ago, writing the names and formulas for salts and molecules. I told you this isn't going away, and it's not. You got to be able to write names and formulas. But guys, when you do this, you're going to do this by balancing charges, just like before. Magnesium's +2, oxygen's -2. You need 1 of each. But guys, here's the rub. Now as you're doing this, you're going to find that as you do this, your equations are going to end up out of balance. So guys, as you're doing this, don't try to balance the equations. Guys, instead of that, what you want to do is just balance the charges. We'll come back and balance the equations later. And guys, we're not going to start with this. We're going to do this later today. So guys, where are we going to start? And the answer is this. Step 3, balance the equations using coefficients. That's for now. That's where we're going to start. But guys, in doing this, you're going to find that these are really, really easy until they get hard. And guys, when they get hard, you're going to be thankful for some help. You're going to find when you're working on your homework, you're going to be like, got this, crap. Got this. So guys, when you hit those stumbling blocks, here are some things that will make these easier. So these are my time-tested hints. These are not going to make any sense to you until I show you what they mean. So guys, hint number 1 is this. Balance polyatomics intact if you can. What does that mean? I'll show you in a minute. Then guys, helpful hint number 2, as you are balancing these things, if you run into what I call an odd-even conflict, because what you need to do is double the odd number of atoms. Because when you take an odd number and double it, it becomes even, and then things tend to work out. Two more. Guys, helpful hint number 3, as you are balancing these things, balance oxygens last. Guys, oxygen atoms are going to be scattered all throughout these reactions, and if you try to balance them first, you're just going to end up spinning in circles. So guys, as you do this, balance the oxygen atoms last. And then guys, finally, the 4th hint is this. When all else fails, trial and error. So guys, when all else fails, revert to trial and error. Throw a 1 in front of the first substance. See if you can get it to balance. If not, erase everything. Try a 2. If that doesn't work, erase everything. Try a 3. And guys, you're literally through trial and error just trying to find numbers that make these things balance. But guys, obviously, if you're going to do that, hint number 5, which I hope you don't need to write. Guys, you got to do these in pencil. If you try to do these in pen, you're going to end up with such a mess that you're not going to know up from down. So guys, always work these things in pencil. Okay, so guys, here's what we're going to do then. I'm going to do one of these for you very, very visually. You're done taking notes now. Guys, I'm going to do one of these for you visually. Then we're going to do, are there 6 of them on there? 5 of them. Those 5 that are on your paper, we're going to do those together. Then, guys, we're going to expand our vision a little bit and solve the one at the bottom. And then, guys, as advertised, you're going to have more than half an hour to work on your homework. Who could it be? Larkin. Here, come to me first. And don't try to catch up, just jump in. Okay? All right, you guys good? Here we go. So, guys, this then is how this process works. So, guys, I picked this chemical reaction to model for you how to do this. And I picked this, and don't write this down, I picked this chemical reaction on purpose because, guys, so much of this is familiar to you. So, guys, let's talk. First of all, this. Which side are the products on, the left or the right? How do you know? The arrow's pointing to the right. So, guys, talk to me about the products. Which of these products is familiar to you? Both of them. Guys, what's this? Water, and then carbon dioxide, right? So guys, we breathe out carbon dioxide. You understand water. Those are things that are very, very familiar to you. Now, guys, let's go over and look at our reactants. Can you talk to me about why this is O2 and not just O? What do we know about oxygen? It's diatomic. It bonds to itself along with the other 6. So guys, you will never see oxygen by itself. It's O2. But guys, at this point, some of you are thinking this. Guys, if oxygen is diatomic, then why is this not O2? It's bonded to something else. So guys, it only has to be O2 when it's by itself. When it's bonded to something else, hydrogen's +1, oxygen's -2. You know the drill. 2 hydrogens, 1 oxygen, that's water, right? So the O2 only counts when it's by itself. Now guys, here's the interesting bit. I chose this reaction because it's familiar, because you know a lot of this stuff. But guys, it's even more familiar to you than this. Every single person in this room has participated in this chemical reaction. I can say that with pretty good certainty. Because guys, do you know what this reaction represents? Remember, equations represent reactions, right? Guys, every single one of you has done this. How do I know? Guys, does anybody know what C3H8 is? No? It's propane. Guys, this is the chemical reaction that cooks your burgers on your Weber grill. You've got that big old white jug of propane, right? And you open up the valve and you turn on the burner and you light that thing. And as you do, these propane molecules come flying out of that propane canister. They react with the oxygen in the air and they release carbon dioxide and water and a lot of heat. And the heat is what cooks your burgers. But guys, the question is this: where does the carbon dioxide go? Into the air. It's a gas. But guys, where does the water go? It's so hot, what happens to it? It boils and it leaves as steam. But guys, when you light your barbecue grill, you are actually making water. And next week, we're going to do this. You can do the math, but I've already done it. If you have a barbecue grill, you know, a standard size grill, and if you light that thing and let it run for 30 minutes, you are producing just short of a cup of water. You're making a lot of water. And guys, that water just evaporates and goes away. But did you guys know this? Our government actually uses that water to hydrate our soldiers. Did you guys know about this? Guys, this is beside the point, but can I tell you quickly? It's like a minute of information. Guys, it goes like this. So this is propane, right? Well, guys, it turns out that propane has an interesting cousin called C8H18, which is actually what is called octane. It is one of the major components of gasoline. And so, guys, the problem is this. When we send our soldiers into hostile environments, have you noticed where most of these hostile environments have been in the last 30 years? Deserts, right? We fight in deserts now. It's kind of what we do. The problem is it's a desert. There's no water out there. So we send these Marines and Army folks off on patrol, and they're in the middle of stinking nowhere. And guys, they got to travel fast and light, and they don't want to lug water around with them. And sometimes they're gone so long they don't makes water. Guys, when our cars run, it also makes water. It's just a different starting point, but it makes water. And guys, you've seen this. Have you ever noticed that on a cold day, it looks like everybody's cars are smoking out the tailpipe? Guys, that's not smoke. It's actually a cloud of water vapor condensing in the cold air. So guys, what our government has done is they have actually figured out a way to condense and collect the water that comes out the tailpipe of our Humvees. And they gather that water together in a bucket, and there's literally a tap on the side of these vehicles, and our soldiers drink the water that would otherwise just be lost out the tailpipe of our Humvees. Isn't that weird? Yeah, but it's really just pure water, yeah. Yeah, 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 yeah. That's a good that's a really, really good question. And so why is it that we die, right? We got to be careful, but yes. So as your car runs, in theory, the only thing that should be coming out the tailpipe is carbon dioxide and water. In theory, the carbon dioxide could kill you because the carbon dioxide displaces oxygen. If we did this long enough, the oxygen would be gone and we'd suffocate. That's not why you die. The reason that we die is gasoline isn't just pure this. There are impurities in our gasoline, and as those impurities burn, they create other substances that can be toxic. But that's not actually the reason that breathing car fumes kills us. The reason that it does is sometimes if our cars aren't burning efficiently, instead of making carbon dioxide, the carbon doesn't completely combust, and we end up with carbon monoxide. And when that happens, that's actually what kills you. Is carbon monoxide is a very, very deadly gas. And none of our cars burn completely efficiently, and consequently, it's the carbon monoxide that does us in. None of that's in the water. All of these things that we've been talking about are gases, and the gases just go away and the water is left behind. And they actually have a little chiller. It's like an air conditioner. Literally is an air conditioner. And as that vapor passes through this air conditioner, it recondenses as a liquid and drops into a bucket. And you literally end up with pure water. Yeah, yeah. Have you guys ever seen that on your air con? Oh, that's a different thing. Never mind. Yeah. Yeah. Right, right. And that's exactly the same idea. Yeah, that's exactly it. You got it. So guys, that was a lot of stuff, right? What are we talking about? I have no idea. So guys, this then is the idea. Looking at this from a distance, where's my clicker? Can you guys see that it's not balanced? For example, how many carbon atoms are going in on the left? 3. How many are coming out? 1. That's a problem. So guys, we're going to fix it. And this is the way the fixing process goes. Guys, just soak this in for a minute. These are representations of the molecules. So guys, what color are the carbon atoms? Gray. What about the hydrogens? Blue. And guys, that's weird, right? Remember when we played with the model kits and we said that the carbons are gray-black and the hydrogens are white and the oxygens are red, and remember water looks like this and all of that happy stuff? The problem is that if the hydrogens were white, they get lost against the background, so they made them blue. So guys, hydrogens are blue and then oxygens are red. So here's propane, here's oxygen, diatomic, here's carbon dioxide. Some of you can even picture the double-double bonds and the linear molecule from drawing Lewis dot structures. And there's our good friend water, it's bent. You remember the story. So guys, the problem is this. We have different numbers of atoms going in as coming out, and we need to fix this. And guys, this is the way that you do this. So first of all, how many carbons are going in? 3. We need 3 to come out. But guys, this is not how we fix the problem. Why not? The reason is this. This molecule does not exist. 2 oxygens cannot bond to 3 carbons. It doesn't work that way. So guys, if we want 3 carbon atoms, what do? The answer is this. We multiply and we get 3 CO2s. And so guys, by putting a 3 right there, getting 3 CO2s, now we have 1, 2, 3 carbon atoms, and that then means we have as many carbons in as out. Do you see how that works? So now let's do this. How many hydrogens in? 8. How many coming out? 2. So what do? Put a 4. And guys, when we put that 4 there, we then have 4 water molecules, which gives us 8 hydrogens. Then guys, how many oxygens in? 2 coming out. Careful. How many coming out? 10. Because we've got 3 times 2 is 6. 4 times 1 is 4. 6 plus 4 is 10. So how many O2s do we need to balance it? There you go. We got 5. Do you see how that worked? So then, guys, we've got 3 carbons, 3 carbons, 8 hydrogens, 8 hydrogens, 10 oxygens, 10 oxygens, and this now balances. You okay with the idea? Okay, now here's the problem, guys. You've got to be able to do that without the pictures. Guys, these are in your notes. Let's do them together. Play along with me. So, guys, this is the way that this works. This is methodical. Start on the left, work to the right, take your time, and guys, you'll be successful with this. So here we go. How many copper atoms on the left? 1. How many copper atoms on the right? 1. How many hydrogens on the left? 2. Hydrogens on the right? 2. Oxygens on the left? 1. Oxygens on the right? That's already balanced. Everything that goes in comes out and vice versa. Guys, the reason that I gave you that is because some of you are getting twitchy right now. And you're going, wait, if there's a blank, certainly I have to write something in the blank. Guys, do not do this. For the same reason that this looks stupid in math, because the ones are understood, you would just write x plus y equals z. Guys, the ones are also understood in balanced equations. Do not write the ones. Okay, so with that said, guys, let's look at the next one. How many aluminums on the left? 1. How many aluminums on the right? Also 1. But now, guys, watch this. NO3. Does that look familiar? What do we call NO3? Nitrate. Guys, this is hint number 1. Hint number 1 says balance the polyatomics intact if you can. So guys, nitrate goes in. Does nitrate come out on the right? It does. So guys, instead of trying to balance the nitrogens and the oxygens, balance the nitrates. So how many nitrates do we have over on the left? 3. So guys, don't do this. Why not? Changes the formula. So guys, what do we do if we need 3 nitrates? Put a 3 in front. Do that with me. Now, guys, we move on. How many sodiums do we have on the left? NAs. 1. What about on the right now? 3. So now we need a 3 here. Then, guys, we go on and we look at oxygen and hydrogen, but maybe something in your brain goes, wait a minute, that's hydroxide. Polyatomic. So then we go, does the hydroxide come out? Yes, it does. So how many hydroxides here? 3. And there we have, and this is balanced. Yep.
Okay, so I don't know if people ever have these, but like, what if there was on the right side, there was 4 LHs, and on the center 3.
Now, so then what would happen is you've got an odd and an even number, and you would double the odd number and start over.
And that's where you like were studying,
Yep, exactly. Yeah, yep. So, guys, you okay on that one? And that's actually where you would end up as least common multiple and build from there, but that's where doubling would actually get you. Yeah. So, guys, try this one. How many potassiums on the left? 1. Potassiums on the right? 1. But now, guys, be careful. NO3. You'll notice that these are building. Guys, does the NO3 stay together? No, it doesn't. So we can't balance the NO3s. We have to do the nitrogens and the oxygens separately. So guys, we go like this. 1 nitrogen, 1 nitrogen. Now what about the oxygens? How many on the left? 3. On the right, left, we have 3. What about on the right? 4. So guys, do you see it? We have an odd and an even number. So how do we fix that? What do we do to the odd number? Double it, but then start over. So guys, what we've got to do is double this and then start completely over. So now we've got 2 potassiums, so now we need a 2. And now we've got 2 nitrogens, and then guys, what about oxygens? How many oxygens do we have on the left? 6, and on the right, we have 4 and 2, which is 6, and this now balances. You okay? 2 more to go. So guys, looking at this next one, we've got 1 iron, we've got 2 irons, that's Fe, so we need a 2. Then guys, we've got 2 H's, 2 H's, notice hydrogen's diatomic, so that's good. Then we've got SO4, and can we balance the SO4s? Yeah, because it's over here as well. So guys, we've got 1 on the left. How many do we have on the right? 3. So we put a 3 here, and now that's balanced. Yeah? No. 1, the hydrogen. But guys, here's the problem. We already balanced the hydrogens. And this is where you've got to be careful, because sometimes balancing one thing will mess up something you already balanced. So you've got to sort of keep the big picture in mind and go, oh my gosh, I screwed up my hydrogens, so now I need a 3 there, and now it balances. You okay? Okay, so guys, 1 more. Hint number 3. Don't ever start with the oxygens. It gets frustrating. Guys, skip the oxygens and do them last. So 1 carbon, 2 sulfurs, 1 sulfur, so we need a 2. Now we can do the oxygens, and we've got 2 on the left, 6, 2, 6. Is that right? We need a 3? Okay. What do y'all think? Guys, that's the process. Start on the left, work to the right, keeping the big picture in mind, balancing polyatomics. You okay? Okay. So guys, one last thing and we're done. What we just did is this. We just talked about balancing equations by using coefficients. Guys, now what we're going to do is we're going to jump up here. We are going to step up to step number 2, where you are not given the formulas of the reactants and products. Guys, all you got to do now is bring forward the information that you learned 2 units ago about writing formulas. We practiced it last unit too. And bring this all together. So guys, there's an example of this at the bottom of your page. Let's do this together. It says this. It says calcium metal, you see it down at the bottom? Calcium metal reacts with copper 1 sulfate to produce calcium sulfate and copper metal. And guys, same process, only now we got to figure out what these things are. So guys, here's what you do. Do this with me. Go right in the middle of your paper, draw an arrow. What you now know is your reactants will be on the left and your products will be on the right. Now you just reread the question, and every time you run into a chemical, you ask yourself, what is it and where does it go? So, calcium metal reacts. Guys, is it a reactant or a product? It's a react. Calcium metal reacts. So now all we got to know is, what is calcium metal? Well, guys, calcium's right there. And it's on the left-hand side of the periodic table, so what does that make it? A metal. So guys, when we say calcium metal, it just means calcium. The fact that it's a metal just tells us it's a metal. But now you'll notice as you read on, it says this, reacts with copper 1 sulfate. What does that make copper 1 sulfate? A reactant. It reacts with that. So guys, here's what you're going to do. Plus. And then, gang, don't do this. Skip a space. Don't draw the line, but in your brain, skip a space. And now we got to figure out what copper 1 sulfate is. Well, guys, copper is Cu. Sulfate is SO4. Copper's +1 because of the Roman numeral. Sulfate's -2. So guys, how many coppers do I need? 2. Sulfate's 1. So this would be Cu2SO4. Then guys, we continue to read on. Reacts with to produce. Hey, now we're talking about products. So guys, calcium sulfate. Calcium's plus 2. Sulfate is SO4 minus 2. How many of each do we need? 1. Skip a little bit of a space. CaSO4. And then, guys, the other product is copper metal, which is just Cu. So now we've written the formulas for the reactants and products. Now, guys, at this point, balance it. So we've got 1 calcium, 2 coppers, 1 copper, so we need a 2. Can we balance the sulfates? Yeah, 1 and 1, and that's balanced.